Dark matter and right-handed neutrinos. A Captain symmetric universe. What is dark matter? It's one of the greatest mysteries in modern science. We know it's there, shaping galaxies, bending light, and making up about 27% of the universe. But what is it? What is this invisible substance that doesn't emit light, doesn't interact with normal matter, and yet holds the cosmos together? Today, we're going to explore a fascinating idea proposed by physicist Neil Turok and his collaborators. It's a theory that connects dark matter to a particle you may not have heard of, the right-handed neutrino. And it's all wrapped up in a bold concept called a Captain symmetric universe. Let's dive in. First, let's talk about symmetry. Symmetry is a fundamental concept in physics. It's the idea that certain properties of the universe remain unchanged under specific transformations. For example, if you flip a coin, it looks the same whether you view it from the left or the right. That's a kind of symmetry. In physics, we have something called Captain symmetry. This stands for charge, parity, and time reversal. It's a deep principle that says the laws of physics should remain the same if you reverse the charge of particles, flip their spatial orientation, and reverse the flow of time. Now, Neil Turok takes this idea one step further. He suggests that the entire universe is Captain symmetric. What does that mean? Imagine the Big Bang, the moment when our universe began. Turok's theory proposes that the Big Bang wasn't just the start of our universe. It was also the start of a mirror universe, running backward in time. In this mirror universe, everything is reversed. Particles become antiparticles, left becomes right, and time flows in the opposite direction. Together, these two universes form a perfect Captain symmetric whole. Pause for reflection. This might sound like science fiction, but the mathematics behind it is surprisingly elegant. And it has profound implications for the nature of dark matter. To understand why, we need to talk about neutrinos. Neutrinos are some of the most mysterious particles in the universe. They're incredibly tiny, almost massless, and they barely interact with anything. Billions of them are passing through your body right now, and you don't even notice. In the standard model of particle physics, we know about left-handed neutrinos, which spin in a specific direction relative to their motion. But there's a possibility that right-handed neutrinos also exist. These would be heavier, more elusive, and they wouldn't interact with normal matter except through gravity. In other words, they'd be perfect candidates for dark matter. Here's where Turok's theory gets really interesting. In his Captain symmetric universe, the Big Bang naturally produces right-handed neutrinos. These particles are created in just the right amount to account for all the dark matter we observe today. It's like the universe has a built-in mechanism for creating dark matter as a byproduct of its symmetry. To understand how this works, let's look at the mathematics. In physics, we describe particles using something called the action. It's a mathematical expression that tells us how a particle moves and interacts with its environment. For a neutrino in curved spacetime, like the expanding universe after the Big Bang, the action looks like this. S equals d4x minus g, I psi overline gm nabla mps minus m psi overline psi. S equals int d caret 4x sqrt g left I overline psi gamma caret mu nabla underscore mu psi m overline psi right. S equals d4x minus g I psi gm nabla mu psi minus m psi. Here, g is the determinant of the spacetime metric. Gm, gamma caret, mu gm are the gamma matrices, and nabla mu, nabla underscore, mu nabla mu is the covariant derivative. This equation might look intimidating, but it's essentially a recipe for how neutrinos behave in an expanding universe. Now, let's zoom in on the Big Bang. At this moment, the universe is incredibly hot and dense, and the spacetime fabric itself is rapidly expanding. In this environment, the equations predict that right-handed neutrinos are produced in large quantities. These particles are stable, meaning they don't decay, and they interact only through gravity. Over time, as the universe expands and cools, these neutrinos spread out and form the dark matter halos that we observe around galaxies today. But there's more. Turok's theory doesn't just explain dark matter, it also makes a bold prediction about neutrinos. In the standard model, there are three types of neutrinos, and experiments have shown that they have tiny masses. but Turok's theory predicts that one of these neutrinos must be exactly massless. This is a testable prediction. If future experiments confirm it, it would be strong evidence in favor of his theory. Now, let's step back and think about the big picture. What makes this theory so compelling is its simplicity. It doesn't require us to invent entirely new particles or forces. Instead, it uses ingredients we already know should exist, right-handed neutrinos, and places them in a framework that respects one of nature's most fundamental symmetries, Kapton symmetry. It's a beautiful example of how theoretical physics can take known principles and use them to solve deep mysteries. Of course, like any scientific theory, this one must be tested. Experiments are underway to measure the masses of neutrinos with greater precision, and cosmological observations are providing new data about the distribution of dark matter in the universe. If Turok's theory is correct, we may soon have the evidence to prove it.